All right, let's take a look at another optimization exercise. Here we have a rectangular page containing 24 square inches of print. The margins at the top and the bottom of the page are 1.5 inches, and the margins on the side of the page, each side of the page, are 1 inch. Determine the dimensions of the page such that the least amount of paper is used. Okay, so we have a page of paper with some specified margins. Here, let's just draw kind of a diagram here. Here, I wonder if I actually, yeah, we have some shapes like this. So we have a rectangular page. Okay. Now with margins, let's see if we can get another rectangle here. Okay, the margins are wider where? Oh, it doesn't really. Let's put it okay, sure. Okay, so we have a page of paper. Now, not drawn to scale clearly because the margins at the top and the bottom are 1.5 inches. So let's just put this distance right here is 1.5 inches. And again, at the bottom, it's 1.5 inches. Okay? On the margins on the side are an inch each. So this distance is 1 inch. Oh, I wonder if I can erase that easily. Oh, that's too much. I was afraid that was going to happen. Come on, come back. There we go. Well, here. Let's do this. Color. White. There we go. All right, 1 inch. We'll say 1. Not enough room to put inch. 1. Okay. Works at 10 inches. So I determine the dimensions of the page such that the least amount of paper is used. So here we're working with area again, but we want to minimize area this time. So okay, let's get some dimensions, some variables in here. So we know that A is, well, if area is as x times y is width times height. So like what is that? And what is that? Okay, well we need to label a few things. A rectangular page is to contain 24 square inches of print. So we could say label, there's different ways to do this, I think, but I'm just going to put an X right there and a Y right there. Now why? Because now we can say that that's where the print is going to go. Like here, blah, 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 blah. Here's where the print goes. Okay, is this rectangular interior rectangle? That's like all the words go. Okay, blah, 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 all right there. And that's going to tell you the area of the print. Okay, now we're told that the page gets 24 square inches of print. So we could say that x times y is 24. 24 square inches of print. Now, if I label that as x and y, what's the width? Well, notice the width, and I'm talking about the page. We're trying to optimize the size of the page. The printed area is fixed, 24 square inches. We're going to try to optimize the overall page. So what are the dimensions? What's the width of the overall page? Well, it's x plus your margins. Plus 1 is x plus 2. What about the height? Again, including the margins of the overall page. Well, it's y plus 1.5 inches plus 1.5 inches, otherwise known as 3. Okay? So those are the dimensions of the overall page. And now the area of entire page, we could say is the overall width times the overall height, which is x plus 2 times y plus 3. Okay? And this is what we call our primary function, or objective function. And by the way, the only other information we have is this guy right here, and that's our secondary function. Okay? So, just like the last example, we have a primary function with x's and y's in. We want a single variable primary function, and we can use the secondary function to do that. Because we could say y equals what? 24 over x. And now we can get a primary function, area function, in terms of x only. So y is 24 over x plus 3. Now, okay, if you differentiate right away, you'll have to use the product rule. I'd probably distribute to get a few different terms. So watch. A equals, okay, x times 24 over x is just 24. Okay, that's nice. X times 3, 3x. 2 times 24 over x, that's 48 over x. And 2 times 3 is 6. And now we can differentiate using the power rule a couple times, and the constant multiple rule, and the sum difference rules, I suppose. If we clean it up just a little bit, we could say a equals what? 24 plus 6 is 30 plus 3x. If you want to get it in the mode to differentiate, we could say plus 48x to the negative 1 power, because I want to use the power rule. It's quicker than the quotient rule. So there's a, my primary function in terms of a single variable now, only x's. So what's a prime? A prime, okay, derivative of 30 is 0, plus the derivative of 3x is 3, plus 48 times the derivative of x to the negative 1 power, which according to the power rule is negative 1 times x to the negative 2 power. Okay? So if we want to now solve a prime equals 0 to find our critical values, so we're trying to optimize here. What is it? It's 3 minus 48 over x squared. I guess I never actually cleaned it up. A prime equals 3 minus 48 over x squared equals 0. Now, to solve this, I'd probably add 48 over x squared to both sides. So 3 equals 48 over x squared. And I'd probably multiply both sides by x squared to clear the denominator. So we get 3x squared equals 48. And now we have a quadratic that we can divide both sides by 3. Let's see, 48 divided by 3 is 16. And then we can apply the square root property and get plus or minus square root of 16. Now, what is x here? Remember, x is the side of print. It's the side of a printed area. In other words, it's a length. Although there's two solutions here, there's plus and minus 4. Clearly, we toss out the negative solution because we're looking for a length measurement. So we only go to x equals 4. Okay, we don't care about the negative solution. Okay, because again, the length is always going to be a non-negative measurement. Okay, now we need to verify that that is a minimum value, a local minimum. So I'd probably use again the second derivative. Is what I would do. So let's calculate a double prime real fast. Here off to the side here. So we think that x, and we'll find the y value in just a second. Let's just verify our x value is correct. A double prime, let's just find the second derivative. Okay, so the a prime is 3 minus 48 over x squared. So the derivative of 3 is 0. Now we want to differentiate, so we have negative 48. Now using the power rule, we have x to the negative 2. So it's negative 2 times x to the negative 3 power, according to the power rule. So a double prime is what? Negative 48 times negative 2, that is 96 over x cubed. So that's the second derivative, a double prime. Now, the second derivative test, the reason I found the second derivative, is the second derivative test can be used to verify that we indeed found the location of a local minimum. So we could say if you plug in 4, a double prime evaluated at x equal 4 is positive. Because 4 to the third power is what, 64? So 96 over 64 is just some positive number. But the important part, so a double prime evaluated at x equal 4 is positive, and the second derivative test indicates alpha d indicates that x equal 4 is the location of a local minimum. Okay? So we have found a optimal value, a value that minimizes this function. Now we've verified that we can look to find our y value. So here, if we know x equals 4, then y equals what? 24 over x. So y is 24 over 4, just 6. So we get y equals 6. So a page that is 4 by 6 optimizes this situation. Oh, no. I was about to double check myself and say, hey, wait a second. And I was a few seconds ahead of myself and realized that is not my solution. So I almost got in trouble here like you would get in trouble sometimes. About, hey, we have a quasi solution, but it's not answering the question. We want to know the dimensions of the page. So what are the dimensions of the page? This is the dimensions. Okay, let's just be specific here. The printed area, 4 inches by 6 inches. Right, that makes sense because the printed area, 24 square inches of print. What about the overall page, though? I think that's what we were actually after. The overall page, well, the width is what? X plus 2, so it'll be 6 inches. And then for the height, it was y plus 3, so 6 by 9 inches. So I guess there's our more complete solution. And then what is that piece of paper? Well, area of paper is what, 6 times 9, 54 inches squared. Okay, so don't get in trouble like I almost did there and say, hey, yeah, we're done. X is 4 and y is 6 because, again, I guess let's read my last sentence. Determine the dimensions of the page. Yeah, dimensions of the page. We do want the overall dimensions of the page there. So you gotta be careful when you're reading there. X and Y, or the dimensions of the printed area, not the page. Okay. All right, that's example for you. Another one in the books. We'll look at a few more examples. Again, trying to get you a varied set of examples because each one is going to be different in its unique way. I'll catch you in the next video.